Hello again. Today we'll talk about YOLO algorithm, which is used for object detection. You can see the demo right in front of you. So this is the app from Ultralytics that does object detection using YOLO in real time. So you can correctly recognize me as a person, and then this is a cup, phone, potted plant. So it's really cool. YOLO is not the most accurate model out there, so it is a bit behind modern state-of-the-art models that just came out in recent years, but it's incredibly fast, which makes it really useful for applications that require real-time object detection when you need to do prediction in less than 1 divided by your frame rate. So it's it needs to be really fast. Also, YOLO is really popular. So creators of the model from the Ultralytics hub itself, they make a lot of effort to propagate the algorithm to masses. So they do open source, they provide tutorials, demos, they have a platform for training and fine-tuning the models. There was a famous story about a kid who was able to fine-tune a YOLO model to predict different toy cars, to recognize and detect different toy cars without writing any code. So it's really cool. So today we are going to actually dive deep under the hood of the model. So what it does, how it's trained, what is the architecture, what is non-maximal suppression, and what is the anchor boxes. So let's go. First, a reminder, I'm making a series of videos about computer vision, so you can check out my playlist. It starts with a simple task of digit classification that I think can be tried by everyone, even without prior knowledge of machine learning. So we start with just 50 lines of code in PyTorch to classify small, low-resolution images of digits. Then in next videos, we have discussed various deep learning techniques to scale up the model, to make it solve more challenging tasks with more classes, higher resolution images, culminating in the famous ImageNet challenge, which is a giant data set with millions of images, 1,000 classes, 150 gigabytes of data, and we actually trained the model to be able to perform really well on that, better than humans, in fact. Then we moved on to object detection task. That is when we might have more than one object in an image. That's one main difference. And we need to predict bounding boxes apart from just predicting the class of an object. And today we are going to discuss an algorithm called YOLO that solves this object detection task. Before we do that, though, I quickly wanted to discuss different motivations behind object detection and current uses in industry and just everyday life. So this picture is from COVID times, where we still had to wear masks. And a startup basically trained a model to predict whether or not a person is wearing a mask. And that is done entirely using object detection. So we train a model to recognize a face and to distinguish a face with a mask and without a mask. One good thing about this is that nowadays making a project like that is quite simple. So you can take one of the existing pre-trained models like YOLO, you can fine-tune it on your own data, something like 1,000 images that you can realistically just collect and annotate yourself. And you would get a working predictor of quite high quality that solves the task that you needed. This is another example from a startup to detect fires. So one of the problems with forest fires is that if a fire starts and it goes unnoticed for some time, it will spread and the area of the fire will rapidly increase, making it much harder to deal with it. And so the startup basically sent out drones to make footage from up high of the forest, and then they used object detection to automatically recognize if there is fire or not, thus informing firemen quicker and being able to deal with the fire easier. And here is another example from my own car actually. So it's nice to see something like that working in real life every time you drive. So obviously, self-driving is not just about object detection. Even just the task of perception is much more complex. So you might want to know distances to the objects. You might want to know the precise 3D geometry. You might need to analyze the speed of the object, and that is solved by a computer vision technique called optical flow. And I'm hoping we will get to that in my channel as well. But even just object detection is still necessary. So we might want to recognize this traffic light or this car, for example. So my car actually emits a sound when it detects that a red light has just changed to green light, which is quite helpful. And obviously the self-driving itself needs to distinguish between cars and pedestrians. And you could see that it does recognize that this is a car here. Here it is on my screen. And it needs to distinguish between cars and pedestrians and just static objects because they behave differently, and the actual control module needs to know that. Okay, so how do you actually do object detection? It's relatively easy to do image recognition. So you start with an image, you pass that through a bunch of convolutions, then maybe a fully connected layer, and then you output what are called class probabilities, class logits. Each of these nodes correspond to just probability of this image containing this class, basically. So it's like one hot encoded vector. If you have 80 classes in your dataset, like Coco dataset has, you would need 80 outputs. And we can sort of just take this hat and just swap it for something else, as long as the thing that we want to predict still can be represented as a fixed number of outputs. So for example, to predict just one bounding box for one object, we can swap this hat for 4 numbers corresponding to the coordinates of the bounding box, and it will still work. So we only need to change the loss for that. So we swap from classification with cross entropy loss to regression with mean square error loss, for example. But now we might have many objects on an image. We can't say that the number of objects is fixed. Sometimes there's just one, sometimes there is no objects, and sometimes there's a lot of objects like here. So we need a model to be able to deal with that. And so what YOLO does is it basically says, okay, I'm going to output a fixed number of objects every time. So this is the solution to this problem. But then the actual number is quite high. So it's something like 10,000 different objects. And so it's enough for most of the pictures that the model might encounter. And this is how it actually works. So YOLO superimposes the grid on top of an image, and then just says that every predicted object corresponds to something in each grid cell. And so the rule for assigning an object to a certain grid cell is where the center of that object lies. So for this human here, this one, the center might be somewhere here, so it will belong to this grid cell here. And so for each of these cells, the model has to output the bounding box coordinates and the class probabilities. So this is like how it actually will look like. So we start with an image, we pass that through a bunch of convolutions, and then we have this cube of outputs where we have a certain grid on top of an image, and YOLO v5 uses 80 by 80 grid. And then each cell within the grid has 85 outputs itself. So 80 for just the classes, so one hot probabilities for classes of all the objects. Then 4 coordinates for the bounding box. And then we also need something called confidence to be able to represent that there is no object in that grid cell. So this is how it looked like for one grid. So we have 4 box coordinates, then we have variable number of one-hot encoded class labels depending on the data set. So for Cocoa, that will always be 18, and then extra 1 number for confidence. So this is how confidence works. So if there is no object in the grid cell, then the confidence should be 0. In addition, and this is the extra point in one of the recent YOLO versions, if there is an object in the grid cell, then the confidence will be equal to intersection over union. So this is a metric of how well the bounding box intersects with the ground truth. And this is an example. So we have this black grid cell here. Then we have the ground truth bounding box for the object that happened to be in that grid cell, and this is in red. And then the green one is the one our model predicted. And so let's say the IOU is 0.73. So the confidence here will be 0.73. So confidence does 2 things at once. First, it allows the model to say that there is no object by outputting C equals to 0. Second, if there is an object, if the model thinks that there is an object, the model also outputs its confidence in how well it can predict the bounding box. So compared to other models, YOLO, which stands for you only look once, the main difference is the speed and just the simplicity of the process. So, for example, one of the previous algorithms called sliding window approach would do something like also dividing the image into grid. So, and then the grid will look something like this. And then you would apply an image recognition detector to the first cell, and then you would slide that window over and apply the same detector to the second cell, and so on. So it takes a lot of inference steps of the model to actually predict, to detect objects for the entire image. Another popular algorithm was called regional proposal network. That is where there is like a 2-stage detector. So first one will have some crude estimations of bounding box for objects. And then the second stage detector goes over each of them and tries to create a precise prediction of what the bounding box should look like. So again, that's multi-stage detector. And YOLO is single stage. So just take the image, feed that into the model, get these predictions for each of the 80 by 80 grid cells, and that's it. So just one inference part of the model. And because of that, YOLO is incredibly popular at the moment for different real-life tasks because it can work in real time. It can work on mobile devices, on embedded devices. So it's really, really popular right now. So some clarifications about how it works, how YOLO works. So first of all, even though we are talking about grid cells like this one here in bottom right corner, every time every node of the output of the model is actually affected by the entire image. And that happens thanks to the sort of power of convolutions. So if you think about this, if you have an image and then you apply a 3x3 convolution to that, each pixel in the output will effectively see 3 pixels in the input picture. If you stack a lot of these convolutions together, the receptive field increases. And so for a deep enough model, you would have the fact that this output that is located in just one grid cell, it will actually be affected by the entire image, which helps the model to use the context of an image, to understand that, this is a field and it might help it predict that this is a dog. In addition to that, an object might be bigger than the cell. So we only look at the center of the object to determine which grid cell should be responsible for recognizing this object. But the object itself can be bigger. That also means that we can increase the quality of the model, or at least the number of objects it can recognize, by making the grid cells smaller, and it still doesn't prevent it from recognizing big objects like this. Also, YOLO solves regression problem, and this is again in contrast to some of the previous models like regional proposal networks that had some crude estimation of bounding boxes. Even though we do have this grid division of the image, the actual bounding box we predict for this man, for example, this is precise. So it doesn't have to precisely align to the grid. It can have arbitrary width and length, and the model will predict the precise bounding box independent of how crude the grid is. And finally, the model itself is fully convolutional. So even though we talk about this 80 by 80 output, and we can sort of think about this as some separate node of the output, the process of obtaining that output is through convolution. That is, applying a fixed filter, a fixed kernel with parameters to different parts of the image to get the output image. Which means that this filter here, the parameters for it are the same when creating this output as well as this output, for example. So even though we have these separate grid cells in the output, the actual parameters used to obtain this are reused across the grid. Now, let's go over the training process and the inference process one more time, just to make sure that we properly understand how it actually works. So we start with just taking an image, then we impose a certain grid on top of that, and then we assign every ground truth object to grid cells. So we don't need any extra manual labeling for that, any annotation. We can always compute the precise center of the bounding box, knowing the bounding box itself, and then decide where to put it in the grid cell automatically without changing the data set. And so what will happen here, for example, is this man here that actually spans several cells. His center is somewhere here, so he gets assigned to this cell here. And then this sheep, for example, gets assigned to this grid cell. Now, here is an interesting part. So here we have two sheep that sort of got assigned to the same cell, which is weird. So one of them would be lost, basically. And also, if we look at this cell here, right, it also sort of looks like a center of the object, because it's almost near the center. But we say that it's not a man. So the model will have to, apart from actually distinguishing, what a man is and what isn't, the model will also need to precisely calculate the center to be able to say that this cell here actually does not contain any objects as far as we are concerned. So the same will happen for this cell, and so on. So all the cells not in gray here will have to say that there's no object there. And again, this is different to what you might see in labeling tasks in one of those website protection services, where you have to say that, okay, this grid actually contains the man. So this is not how YOLO works. YOLO will say that this grid does not contain a man. So this is contrary to how many of us are used to. And then during inference, we start by just feeding in the image to the model and getting these 80 by 80 grid predictions with confidences, class probabilities, and actual bounding box coordinates. Then we filter out everything below a certain confidence threshold, and it might look something like this. And then we get the actual bounding box prediction for every object that still remains. So as you can see here, we only recognized one sheep because these two sheeps happen to be in the same cell. So one of them, the model has no way of saying that there are two objects in the cell. It always says that there is one object. And also, since this cell here almost looks like it should contain the center of a man, as well as this one here, we have a duplicate prediction for the bounding box of the man here. So we have two bounding boxes mostly overlapping for the same object. And to deal with that, we use a technique called non-maximum suppression, which acts as a post-processing step. So after we got the predictions for the model, we apply this NMS, which just looks at all the bounding boxes that overlap with IOU above a certain threshold, and then we delete all the duplicates. And to decide which duplicate to delete, we actually look at the confidence. So we take the one bounding box that the model is most confident in, which is one of the reasons we needed these confidence in the first place, to actually be able to distinguish bounding boxes that the model might just be guessing to the ones that are like the model is really sure in. Unfortunately, this non-maximum suppression might have false negatives, especially in cases where there's a lot of overlapping objects, a lot of objects falling on the same grid cell. So like this picture here, we have a lot of people and they're not really separated from each other in terms of, the just level of overlap of the bounding boxes. And because of that, this man, for example, is not recognized. And this is basically because of this NMS step. So the model itself might be able to detect this man as a man, but this bounding box overlaps too much with neighboring objects, so it gets deleted on these post-processing step. In later YOLO versions, there was another introduction called anchor boxes that helps deal with the case when we have a lot of objects of different shapes whose centers are in the same grid cell. So, for example, here we have a car and a man, and the actual shapes and bounding boxes for them are completely different. But then the car and the man, the centers are really close together and they fall in the same grid cell. And because of that, the model really has no way of saying that, this grid cell contains two objects. So the way the anchor boxes work is we have several anchors, which are basically the predefined shapes for the bounding boxes. And we have like 3 of them, for example. So one corresponding to different scales, different aspect ratios. So they might be small, they might be really big, and they might have something that is like wide, and then something that is more tall. And so what happens during training is every ground truth object is first matched to a grid cell, and then within that grid cell we might have 3 different anchors, and we match the ground truth object to these anchors to see if this man, for example, matches more with the anchor that is tall than with the anchor that is wide, for example, and then assign the man to one anchor, and then the car will be assigned to the second anchor. But the actual matching rule is quite wide, so we take the width or height of an object divided by width or height of the anchor, and that ratio can be from 0.25 to 4. So it's quite a wide range of possible matches that we can have. And so the model will predict 80 by 80 by 3 boxes. So for every grid cell in an image, it will additionally predict 3 predictions for different anchors. So the way that helps is twofold. So first of all, we now have this notion of having several different objects in the same grid cell. In addition, it allows the predictions to specialize. So we might have a head in the model that focuses mostly on quite big, tall objects, and another hat that focuses on wide objects, and that allows them to specialize more and to train with higher accuracy. Now, finally, let's talk about the loss used for actually training the model. So YOLO has 3 terms in the loss. The first one is responsible for correctness of the actual bounding box predictions. So one way to do that would just to calculate the mean squared error loss, which is regression, basically saying that for a predicted bounding box, each of the coordinate, how far it is from the ground truth. And then YOLO v5 uses the actual IUU, so the measure of overlap of the bounding boxes, the predicted one and the ground truth one. IUU itself is not differentiable, so it cannot be used as a loss. And so YOLO v5 uses a variant of that called C-IUU, which is slightly different to make it differentiable. Then the second term is cross entropy, which is just to measure the correctness of classification. So the model will output, for every class, it will output the probability. So for every grid, for every anchor, it will output probability of every class, and then cross entropy will measure how well that corresponds to ground truth. And finally, objectness. So objectness wants the model to output correct confidence scores, and the confidence scores must be 0 if there is no object, and then if there is an object, it must be equal to or as close as possible to the measure of correctness of predicted bounding box. And so another way to look at that is to imagine like how many predictions we actually have. So in this image, we have 7 objects, so 5 sheep, a man, and a dog. And so the first 2 losses, 2 terms in the loss, will only be defined for those grid cells that actually contain these objects. So 7 grid cells here, only for them we will have the IU loss and the cross entropy loss. Whereas if the actual grid is 80 by 80, and then for every grid cell we have 3 anchors, that's like 20,000 grid cells. And we want each of them to say that there is no object here. So no object here, 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 and so on. So there is a lot of predictions, and all of them has to say that there is no object. Otherwise, we would have a lot of noise in the background saying that there are random noise, random objects that are not there. And if the model does that, the first 2 terms in the loss will not change. So these 2 terms are completely insensitive to these false positives in the background. And only objectness will say that for this grid here, for example, there was supposed to be no object, but the model predicted that there is an object, so it will penalize that. So objectness loss term is the only term that can reduce this background noise. And now let's look at results. So this is the screenshot from Papers with Code website, which is basically a history of all the state-of-the-art submissions for object detection on COCO dataset. So it started in 2015, and we can see that the progress of the science was overall incredible, going from 20 to 66 in 2023. And so YOLO is somewhere here. So the blue dot here is YOLO. Its current best MAP on COCO dataset is 56, whereas this codator model from 2023 is 66. So YOLO is a bit behind in terms of accuracy, but it is still a really good model, mainly because it's fast and it's single stage. So it's fast during inference. So you just need one stage, you feed in the image, you get the prediction, and just a quick post-processing step, which allows it to work in real time, which is really good for applications like self-driving, so robotics, and so on. Also, the model itself is quite lightweight, so Some of the models weigh like 100 megabytes, so it's quite easy to put that on a mobile device, on embedded device, and the training is quite easy as well. Main drawback of the algorithm is the accuracy. So it is behind state of the art at the moment. And also it has some fundamental problems that it cannot deal with. So anything that has a lot of objects cramped together in a narrow space, anything that has a lot of overlapping bounded boxes, for these cases, the YOLO algorithm will always be quite bad. So think about flocks of birds, crowds of people, stuff like that. We'll always have misclassifications. Another problem with the approach is the complexity. So the code for the model and for all the components like the anchor boxes, this grid matching, the non-maximal suppression, it is quite complex. And also, we need to have some prior knowledge of the data. So anchor boxes have to match potential objects in an image. And then if we have some unexpected aspect ratio that is quite far away from expected anchor boxes, the model will not be able to recognize that. And this is not good. We want to have the model that is like a black box. We just throw it in, it trains on some data, and it outputs good results no matter what the data is. So we want that. And YOLO is not like that, unfortunately. So this concludes the video for now. In the next video, we are going to read the actual code of YOLO v5 implementation. So we'll look at the precise architecture for the model, we'll look at the training code and the image transformation that were used for data augmentation and all of that. So stay tuned.